about scale in geography. Scale is really important. It's one of the fundamental things that run through physical geography and cultural geography. What do we mean by scale? Why is it important? Why should we care about it? That's what we're going to talk about today, is why scale matters in geography. Let's briefly talk about the concept of scale. Understanding geography requires a sensitivity and awareness of scale. This provides a framework for understanding how events and processes influence each other. In geography, we must be cognizant of the fact that any phenomenon we are studying at one scale can be influenced by developments at other scales. For example, take a look at traffic patterns. They affect local neighborhoods, also how we walked across the street this morning, but also can be studied regionally, are also affected by national or international migration, economics, and even the median age of a population. Climate is another phenomenon that is immensely complex, operating at multiple scales. For example, it operates at a local scale, everyday weather, affecting local storms. But it also operates at a global scale, affecting such things as ice pack at the poles, sea level, the locations of deserts and rainforests, monsoons, and so on. In between, at a regional scale, climate is affected by landforms, such as mountain ranges, prevailing winds, and even eruptions of volcanoes. Thus, we must fully look at processes operating in multiple scales to fully understand what's going on. Scale is about size. It can be relative or absolute. Scale can be about space or about time, since things that occur across space almost always have a temporal component. For example, think about wildfires versus glacial advance. They have different spatial scales and different temporal scales. There is also a thematic scale, having to do with the grouping of attributes, such as water quality or weather variables. Scale is a theme that runs through all of geographic analysis, because geographic analysis has to do with trends, patterns, and relationships across space and often across time as well. Several kinds of scale exist in geography, and no, none of them have to do with the scale that measures how much things weigh. Cartographic scale refers to the size of a feature on a map relative to its actual size in the real world. More about that in a bit. Analysis scale refers to the size of the unit at which a particular problem is analyzed, such as on a scale of a watershed or a neighborhood. Phenomenon scale, as referred to by Daniel Montello, refers to the size at which human or physical earth structures or processes exist, regardless of how they are studied or represented. They are all interrelated. For example, choices concerning the scale at which a map should be made depend in part on the scale at which measurements of Earth features are made and the scale at which a phenomenon of interest actually exists. Scale matters in lots of ways. How do we figure out how large these buildings should be when we build them? What about the shading that the surrounding buildings would experience if a certain building was constructed? What about the scale of traffic on these streets? What about the width that these crosswalks need to be? So what kinds of standards do we need for everything that we build on the landscape? Also, scale matters when we're representing the real world onto a two-dimensional paper map or map on metal, or on a two- or three-dimensional computer screen in a geographic information system. How do we represent this onto here? What is the scale factor required? That's what we'll talk about next. Cartographic scale. If you made a map of your classroom at 1:1 scale, how big would it be? the size of your classroom. Obviously, that would be really clunky. Hard to fold, too. So we reduce the scale of the Earth to fit it on a map, whether it is a paper map or a 2D or 3D representation on a computer screen, such as in a geographic information system, or GIS. We use a representative fraction, which is a ratio of the map distance to the Earth distance. For example, a map at 1 to 10,000 scale means that one unit on the map represents 10,000 units on the Earth. The units can be whatever you want them to be, but they need to be the same on each side of the fraction, or ratio. So, 1 centimeter on the map represents 10,000 centimeters on the ground, or inches, or meters, or whatever. Cartographic scale can be expressed as a verbal statement, such as 1 inch equals 1 mile, or graphically, in a scale bar, for example, or as a representative fraction, such as 1 to 24,000 scale, which is the scale of a standard USGS topographic map. As the size of the represented Earth gets larger, the representative fraction gets smaller, i.e., the denominator gets larger. Hence, a large-scale map shows a relatively small area of the Earth in great detail, whereas a small-scale map shows a large area, but in a coarser detail. Think about it this way. Which is more, 1/10 or 1/10,000th? 1/10 is more, right? Which would you rather have? A fourth of a pizza or a 100th of a pizza? A fourth is more. The denominator is smaller, but the whole quantity is larger. 1/10 or 1 over 10 could be written as 1:10, or a 1 to 10 scale map. To clarify, I often use fine scale and coarse scale, or lots of detail or not very much detail. To sum up, a large-scale map shows a large amount of detail. The confusing thing is that when we discuss large-scale phenomena, we are usually referring to things operating on a large scale or a large area, like hurricanes. And if we were to map all of the hurricanes in a year, over the course of the year, across the North Atlantic, for example, the map that we would make needs to be at a small scale to show all of those hurricanes. Here's an example of how scale matters. Let's take a look at median age of the population. I'm going to use ArcGIS Online to do that. At a certain scale, there's one state that stands out as far as being less than other states as far as the median age. Let's take a look at the legend. Oh, less than 30 over there in Utah. Let's zoom in though. When we get into the county level, we see that, again, scale matters. I see certain counties that have a lower median age than other counties. Why is that? What are the economic and other forces that act as suppressors of the median age and also act to raise the median age? For example, if I zoom into Boulder County, Colorado here, I see that all of Boulder County at a certain scale has 1 median age. But if I zoom into the county level, then start zooming into the sub-county level, I'm going to start seeing neighborhoods. And even in Boulder County, I can see that there are certain counties in the mountains that have a higher median age. But if I zoom into the city of Boulder, particularly those neighborhoods near the University of Colorado, which sits right here where my mouse is pointing, those neighborhoods indeed have a lower median age. So even at this scale and at other scales, scale matters. It depends on the phenomenon that you're studying. Here we're analyzing median age, and we see that indeed scale matters. Let's look at another example. Let's take a look at USGS topographic maps. At a small scale, I can see some major landforms. I don't see a whole lot of detail though. But as I zoom in to a larger scale, pause right there, I see some larger landforms. Okay, interesting. I can see Lake Tahoe here, for example. If I zoom in a little bit more, I'm going to start to see some content. This is content from the 1 to 250,000 scale USGS topographic map series. If I zoom in a bit more, I'm still seeing the 1 to 250,000 scale series topographic map content. Now I'm seeing the 1 to 100,000 scale series as I zoom in to South Lake Tahoe. Let's zoom in there a little bit more. And as I keep zooming in, I'm seeing the 1 to 24,000 scale series right here on the California-Nevada border. Now I've got a very large scale map. I can see a great amount of detail, right down to the contour lines, as you can see right here, and the different features such as the beach, the marsh, and some of the commercial and residential development occurring along the lake. You know, most maps have a scale bar. For example, this one right here, it says 1 to 24,000 scale. So that's the text representation of the scale. Then there's a bar that actually gives you distances. For example, this distance on the map is 1 mile on the ground. It also has a couple of other things on it. For example, it has a scale in feet, and it also has a scale in meters. So for example, this distance is 1,000 meters on the ground, or 1 kilometer on the ground. So this is a scale bar, and most maps will have a scale bar. It's one of the important things about a map, because it tells us how detailed the map is. It tells us how much of the map is represented by how much area on the Earth. Scale also matters with regard to topographic maps. I've got a USGS 1 to 24,000 scale topographic map here. It's got a scale bar at the bottom. At this scale, 1 to 24,000, it would require 55,000 of these maps to cover the whole country. And that is about 232 times 232 maps. So roughly 464 feet north-south by 234 feet east-west. So laid out end-to-end, that would cover multiple football fields. At a smaller scale, let's say 1 to 100,000 scale, it would require fewer maps to cover the country. At a larger scale, let's say 1 to 10,000, it would require more maps to cover the country. So scale matters with regards to topographic and any other kind of map. Right now I'm analyzing some watersheds inside ArcGIS Explorer. The watershed scale that I'm looking at right now is a good one. These red boundaries are the watershed boundaries. These blue lines are the major streams and rivers that flow into and out of the individual watersheds. Choosing the right scale is not as easy as it seems. You really have to be cognizant of all the things that we're discussing in this video, and I encourage you to seek out additional resources. Now, soil is a good example of something that can be studied at a really local level. Now, there are some geographers that want to know what kind of soil type this is. And there are others that want to look at soil across whole regions and how this soil becomes weathered from the superficial geology, which is underneath. So we can look at soil on an extreme local level. We can also look at it on a regional scale or a continental scale. So just soil, for example, touches on lots of different scale issues in geography. When we think about scale, we usually think about vast distances, and one of the ways we measure those distances is with a telescope. Scale matters in geography and astronomy. Look at the size of the Earth related to other smaller planets. Now look at the size of the Earth related to all the planets. Look at the size of the Earth now in relationship to our Sun. Now look at our Sun related to other stars. Now look at our Sun related to still other larger stars. Scale matters. One of my all-time favorite resources to teach about scale is the movie Powers of 10. Keep an eye on the scale at the bottom, and also how the images rotate or seemingly cycle between lots of activity and not very much activity. Still at the subatomic level here. DNA. Now we're at the nucleus level and cell level. Now we're starting to see a leaf. Now a satellite image, zooming out to smaller and smaller scale, seeing more and more area. Now the whole solar system. Milky Way galaxy. In geography, scale is important far beyond the map. It is important in deciding what scale to analyze a problem in the first place. For example, for analyzing river systems, is it most appropriate to study whole drainage basins? Or should you select a sample of watersheds? For languages, do you study dialect areas or whole language regions? We often use terms such as local, micro, meso, macro, and global in discussing scale. The idea of nesting is also important. Blocks, for example, nest inside block groups. Block groups nest inside census tracts. Census tracts nest inside counties for U.S. demographic analysis based on U.S. Census Bureau geography. That features and phenomena are interrelated at a variety of scales is also a theme running throughout geography. Sometimes we have to generalize features and phenomena to really see a pattern, simply because there is too much detail at a local level. In other words, we want to see the big picture. So generalization has to do with scale too. Conversely, if we want to study human spatial interaction at something like a sporting event, or maybe commuting patterns within cities, we may very well might want a great amount of detail. So scale matters. Issues of scale are all around us. Literally. What issues do you identify here? What does this area look like at a small, medium, and large scale? And what natural and human-caused forces operate at each of those scales? This is the Front Range of Colorado, the intersection of two enormous ecoregions, the Rocky Mountains to the west and the Great Plains off to the east. What sort of plant and animal species dominate in each of these ecoregions? I'm looking out over the short grass prairie that dominates the western or highest part of the Great Plains. But these mountains off to the west, as you can see, are dominated by spruce and pine trees. What is the scale of these plants, and what is the scale of these ecoregions? What is the height of each of these plant species? How much land area do each of these ecoregions occupy? What is the scale of these mountains? How tall are they? How far north and south do they extend? How does their scale affect the climate, the vegetation, and the land use of this area? It turns out that scale matters. I'm standing now on the leeward side of these mountains in the rain shadow. Why do we not see such a vast amount of short grass prairie? Humans obviously have extensively modified this environment as far as the eye can see. Humans have affected the land, but the land affects humans as well. For example, this area is semi-arid, even in the mountains. When we build in the mountains, which are naturally in this area prone to wildfire, lives and property are affected. Indeed, we have had several fires already in this area in 2011. And in 2010, about 7 months ago, we had a massive one called the 4 Mile Canyon Fire that scorched 6,100 acres and destroyed 169 homes. Fighting the fire alone cost $10 million. Where does the water come from for industrial, residential, commercial, and agricultural use? We've modified the land, even way up there in those mountains, to bring water here. We've diverted it from the western slope to the eastern slope. This is a massive effort that's occurring on a big scale around the world. And you can bet that it's economic and also political as well. This environment is undergoing rapid change. It's one of the most rapidly urbanizing areas in the country. Why is that? What's the scale of the urbanization here and around the world? On a local scale, what is the land use like here? This neighborhood is primarily high-tech industry, office park with condos and shopping areas off to the west. How did the land use evolve in this area? Was it purely a local scale phenomenon, a sub-regional scale, amenities being close to the mountains, close to the University of Colorado, close to mass transit, to that freeway off to the north, or a supra-regional or even a national scale phenomenon? That is, economic and lifestyle forces bringing people to Colorado. These are just a few considerations to point out that here and everywhere, scale matters. Where does the water come from? Residential, commercial, and industrial, and agricultural use. We have modified the land, even way up here in those. Where does the water come from for residential, commercial, agricultural, and industrial use in this area? Where does the water come from for industrial, commercial, agricultural, and residential use? We have modified the land, even way up there in those mountains. Have you ever thought about this? Where does water come from?